So this week lecture is on classification technique. And if you can remember, last week we covered linear regression model, which assumes that the response variable y is numerical or quantitative. But as in many situations, the response variable can be categorical or qualitative. For example, like gender or between success and failure, or the eye colors and etc. So when we try to predict a qualitative response where the y variable is categorical, it means that we try to classify this observation into one or more categories. And this classification technique involves assigning the observations to a category or a class. And it is often the methods used for classification. First, it will predict the probability of each of the categories for the qualitative variable as the basis for making the classification. So what it means here is that it behaves like regression models where you regress some categorical variable over the predictors, and then you try to predict what would be the probability. And based on the probability value, we're going to assign whether this belongs to, whether this observation belongs to any one of the category that we are interested in looking. So there are three most widely used classification technique. Number one is the logistic regression and the linear discriminant analysis. We also have quadratic discriminant analysis and the k-nearest neighbors. And for this lecture, we are going to particularly focus on the logistic regression, which is the most commonly used classification technique. So before we venture into the technicality, it is good if we can see some of the examples that calls for classification techniques. So let's look at the first example. A person arrived at the emergency room with a set of symptoms that could possibly be attributed to one of three medical conditions. So the goal here is based on this predictors, based on this independent variable, the set of the symptoms, okay? And we're trying to predict whether this person falls or belong to any one of the three medical conditions. So in this way, this calls for a classification technique where we try to classify this person based on his set of symptoms. And in this problem, we have three levels of the response variable. We have three different conditions. And let's look at the second example. An online banking service must be able to determine whether or not a transaction being performed on the site is fraudulent on the basis of the user's IP address, past transaction history, and so forth. So for this one, it calls for the classification technique because we try to classify a customer based on the user's IP address, the past transaction history, and other predictors, and we try to classify whether this customer is fraudulent or not. So in here, we have a binary response variable. And in the third example, on the basis of DNA sequence data for a number of patients with and without a given disease, a biologist would like to figure out which DNA mutations are deleterious or the disease causing and which are not. So basically here, we would look at the DNA sequence and we try to classify whether these DNA mutations are deleterious or non-deleterious. So there's a binary category for this one. So all this example calls for a classification technique because obviously the response variable are categorical. So now we know that the linear regression is not an appropriate tool for qualitative or categorical response, but now we want to understand why. I'm not going to talk a lot about this, but it is important that you know, at least you know why this is not a suitable, why linear regression is not a suitable tool for categorical response. Let's look at this example. Let's say we try to predict the medical conditions of a patient where the response variable is equal to 1 if this person has a stroke, and 2 if this person have a drug overdose, and 3 for epileptic seizure. So the problem with this one is that let's say you have a set of explanatory variables and you try to use the linear regressions to predict whether this person is 1, 2, or 3. Okay, so the problem is that The coding implies that the drug overdose is between stroke and epileptic seizure. So the higher the value for the response variable, you would think that this person might have an epileptic seizure. The lower value would be stroke, and you believe that between stroke and epileptic seizure, drug overdose is in the middle, which is not true. Okay, because this is like a nominal variable. It's totally different thing. It's not like have a ranking of the lower and the middle and the higher levels. And using this coding also, we would assume that the difference between drug overdose and stroke is the same as between drug overdose and epileptic seizure, because between 1 and 2, the difference is similar to the difference between 2 and 3, which is exactly not true. And another problem is that for one researcher, you might want to use this 1, 2, 3 as in the slide here, okay? But another researcher might want to use 1 for epileptic seizure, and 2 for drug overdose, and 3 for stroke, or the other way around, or whichever way, okay? So different coding will imply totally different relationships. The output that you're going to get is totally different. So how do you want to, really understand what caused a person to be classified as stroke, what caused it to be classified as drug overdose and epileptic seizure? You can never do so using a linear regression. However, if you have a binary response variable where your response variable y only have two categories, 1 and 2, success and failure, male or female, something like that. So perhaps there are only two possibilities for the patient's medical conditions, stroke and drug overdose, where y is equal to 1 if this person is drug overdose and 0 if this person has a stroke. So for this one, we could fit a linear regression by the least squares to this binary response, and we can predict the drug overdose if the predicted or the estimated response variable is larger than 0.5. So this 0.5 is actually the predicted probability. So if the probability is high, and you need to remember that the probability must be between 0 and 1. So if the probability is above 0.5, then we would predict and we would classify this observation to belong to drug overdose. Okay. So, but there is a problem with applying the linear regression for categorical data, even if it is a binary. So let's talk about it by using this example. So for this example, we're going to use the default data set, and the goal is to predict whether an individual will default on his or her credit card payment on the basis of the annual income and monthly credit card balance. So here we have two X variable, which is income and the credit card balance, and the response variable is a binary response variable, which is default or not default. So the logistic regression models the probability that y belongs to a particular category. So before we do the modeling, it is good if we can visualize the data just to understand the relationship between the three variables that we have here. Okay, so the first one on the left hand side, you can see the scatter plot between balance and income. And the colors actually symbolize whether this individual is defaulters or non-defaulters, where individuals who defaulted in a given month is in orange and those who did not is in blue. So if you look at the balance, the credit card balance, you can see that the higher the credit card balance, the higher probability that this person is going to be defaulters because it is in orange. But if you look at the income, whether you have a low income or you have a high income, there's no clear way of to determine whether you will have higher probability to become defaulters. Okay, so this one tells us that income may not play a role, but balance definitely will have explain about the difference between defaulters and non-defaulters. And let's look at the box plot on the right hand side here. So here we have the box plot against the response variable. So again, if you look at the income, there's not so much different between defaulters and non-defaulters. But for the account balance, the credit card balance, you can see that those who are defaulters will definitely have a higher credit card balance to those who are not defaulters. Okay, the next slide here tells you two models here. On the left hand side, we have a linear regression, and on the right hand side, we have a logistic regression. So if you look at the linear regression, first I'm going to talk about this 0 and 1 for the probability of default. So probability of default equal to 0 if this person is non-defaulters. So this means that y is equal to 0, and this is y is equal to 1, which means that these persons are defaulters. So if you look at the between the balance and the probability of defaults, definitely you will see a pattern here where those with a higher balance, they are a little bit on the right hand side compared to those with a lower credit card balance. However, if you try to fit the linear regression here, which is a straight line, you can see that the problem with this linear regressions is that some of the probability is negative. So how can you have a negative probability? Okay, so for if you have the credit card balance of less than 500, then the probability of being default is negative. So it is impossible. And if you look at the higher part here, this is higher than 2,500 for the credit card balance. The probability of being a default is just a little bit over 0.2 or maybe 0.3, which is a low probability. So now we look at this balance 2,500 and we go back to here. If you put a straight line here, you can see that those with the credit card balance above 2,500, they are almost exclusively consist of defaulters. None of them are non-defaulters. All of them are orange. Okay, so how can you say that this person will have only 30% probability of being a default? So this is a problem with the linear regressions. Now we would like to look at the logistic regression. Now this is better, because one thing is that using the logit function, it will always give us the probability of between 0 and the maximum of 1. So there's no negative probability, there's no probability above 1. And the thing is that we can see that okay, it captures the data quite well. Okay, for most of those with an income of less than 1,500, the probability of being, okay, we look at the cutoff value here, which is 0.5 here. Okay, so most of them are actually non-defaulters, which is good. Okay, but and then after the probability of 0.5, it goes up here, and we are able to capture most of the defaulters. Of course, there's a misclassification because our model cannot capture the data 100% of the time. But we can say that the logistic regression is doing a much better work than the linear regression on the left-hand side. So now let us talk about the logistic regression. So one thing is that the probability must always range between 0 and 1. So this one, what it means here, PR is for probability. So this is the response variable default. So if default is equal to 1, or y is equal to 1, or default is equal to yes, given the balance. So this is the predictor variable. If you have more than one, you can just list down here, okay, balance and income. So the probability must always range between 0 and 1. So for any given value of the balance, we can predict the default if the probability of balance is larger than 0.5, then we might predict default is equal to yes. Okay, so what if, okay, this is a question of practicality. Let's say someday you're working in a bank, okay, and you're being assigned to make a classification technique based on the customer's data, and you want to make a decision based on the applications of customers' application, where maybe they apply for a credit card or any loans, and you want to make a decision whether you want to approve the loan or not. So maybe you can use their information such as their income and also their credit card balance and other information. And then you're going to make decision, and the decision is based on the threshold value that you're going to put. So you can use the threshold value of 0.5, which means that if a person have 50% or 51% of being a default, you would disapprove the loan. So if the person have a less than 50% probability, then you're going to accept the loan. However, if you want to try to avoid risk as much as possible, let's say even if this person have a 20% chance of being a defaulter, you do not want to accept this person, then you can put a lower threshold, example like 10%. So you only accept 10% of the customers. Oh, no, no, no. What I mean here is that you only accept customers with a 10% probability of being a defaulter. So this is a very low threshold. So this is basically based on the domain knowledge. And okay, I'm going to talk about this, but it is it is very helpful if when you look at this technicality and you want to understand more, you can look at the book, because as I told you, the book is available. The ebook is available online. You can search for it and you can download it, and then you can read the book. So if you want to study more about the technicalities, please read the book. Because in this lecture, I'm going to just throw away some of the formula, but our focus is more on the R coding. Okay, so we might just like, as long as you understand here this thing and that thing, you don't have to really memorize it. But our focus is on the lab session basically, and how you interpret the results. Okay, I'm going to talk about this. This is taken from the book. So this is the okay. So the first one is actually the logistic function, where you have the probability of x is given by the exponents of da 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 divided by 1 plus the exponent of da da da. Okay, and a little bit of manipulations. You can have px divided by 1 minus px equal to the exponent of beta naught plus beta 1x. And to get a linear versions of this part, okay, you take the log from both sides. So on the left hand side, this will become the log of this bunch, which is equal to the log of e become the power itself. So when you have this format, what you're going to say is that you can say that this part on the left hand side have a linear regression. Have a linear relationship with the part on the on the right hand side part. Okay, so this look very familiar. This looks like linear regression. But except that instead of having fx or y here on the left hand side, here we have the logit function. So this is called the logit function. So the px here, this part, the px over 1 minus px is called the odds, and it can take on any values between 0 to infinity. So it can never be negative. So the interpretations here is what you can say here is that if px is equal to 0.2, which is 20% of the population, or 1 in 5 people, this is the same statistic. 20% is 1 in 5 people. 1 in 5 people will have the odds of 1 over 4. So how do we get the odds? So if px is 0.2, and then we plug in px into this formula, 0.2 over 1 minus 0.2 is 1 over 4, or 0.25. Okay, another example is that if px is equal to 0.9, which means that 90% of the population will be 9 times more likely to be a default. Okay, will have an odds of 9 to become a defaultess. So if px is equal to 0.9, so this is 0.9 over 1 minus 0.9, which is 9. Okay, so if we take the algorithm, this one, okay, this is what I explained using this one. So we take this algorithm on the odds here. Okay, we have the logic function, which is the log of px over 1 minus px, and then we're going to have beta naught n plus beta 1x on the right hand side. So the left hand side is called the log odds or the logic function, and the logistic regression model has a logic that is linear in x. So what it means here is that on the right hand side you can see that this logic function on the left hand side, it has a linear relationship with x. Okay, so instead of the linear regression where you have y equal to beta naught plus beta 1x, in which you can say that x and y have a linear relationship, now instead of x and y, we have x and the logic function. So x has a linear relationship with the logic function. So the interpretation that you can make here is that increasing x by 1 unit changes the log odds by beta 1. So 1 unit increase in x will increase or will change this logic function or this log odds by the amounts of the coefficients beta 1. Or equivalently, it multiplies the odds by the exponent of beta 1. So if let's say beta 1 is equal to, okay, let's say, I'm going to make this zoom to 100 so you can see. Let's say beta 1 is equal to 0.975, okay? So the odds, okay, the odds of beta 1 is given by the exponent of beta 1. So the odds here, odds ratio, is given by the exponent of beta 1, which is 2.65. So we can say that those with is 2.65 times more likely to become . Okay, I'm going to explain about this in the using the real data later part, okay? And then for this one, if in the linear regression that we covered before, we use the least squares methods. And for this one, we use the maximum likelihood to fit a logistic regression model. So if you can remember the least squares, what we do is that we try to minimize the residuals. So the actual y minus the estimated y. Okay, so we try to reduce the residual, so that is why it is called least squares methods. But in a maximum likelihood, what we do is we try to maximize the likelihood, and the likelihood is given by the L function here. So L, the likelihood of beta naught and beta 1 is given by the sum product. So this symbol is the sum product of the px multiplied with the sum product of 1 minus px. Okay, so the maximum likelihood seeks to estimate for beta naught and beta 1 to find the beta hat naught. Beta hat is the estimated beta hat, and beta hat 1 is the estimated beta hat 1. Okay, so this beta hat, when you have a hat, which it means that this is that an estimate value for the beta naught. So beta hat 1 is the estimated value for beta 1. So maximum likelihood seeks to estimate the beta naught and beta 1 such that plugging this estimate into the model for px will yield a number close to 1 for all individuals who are defaulted. So what you try to do here is that this likelihood, you try to maximize this likelihood so that the px here will yield a number close to 1 for all individuals who are defaulted, and a number close to 0 for all individuals who did not. So if you have a certain characteristics, okay, and let's say this person is defaulted, so you want to be able to predict that this person will have a high probability to be defaulted. But if this person is not a defaulter, you try to find the beta naught and beta 1 that try to predict that this person will not default. So let's look at these results. Okay, so this is a result for a logistic regression with only one predictor, which we have a balance here, 0.0055 is the coefficient, and we have the intercept value here. So the estimated coefficients for the balance, or the beta hat 1, is 0.0055. It means that the unit increase in balance is associated in the increase in the log odds of default by 0.0055 units. So you need to remember that this is actually based on this relationship. The beta 1 is 0.0055 here. So 1 unit increase in x will increase the logit function, the logs odd here, by 0.0055. But if you really want to know the odds ratio, okay, so we just 0.0055 here, and remember this is the exponent of beta 1. So the logs, the odds ratio is 1.0055. All right. So that is for the coefficients, and you can see the standard error here. The standard error measures the accuracy of the coefficient estimates, and the Z statistic is similar to the T statistic in the linear regression output, and the large Z value indicates the evidence against this hypothesis. So the p-value is very significant, and the Z statistic is also very big, okay, compared to the standard error. And the standard error, which is very small, divide by the Z statistic, we're going to expect that the p-value is going to be very, very, very low. So if the p-value is very low, we are able to reject the hypothesis that says that beta naught is not significant. So once we reject this, then we would say that the balance is significant in explaining the relationship. This balance is a significant variable to predict the default status. Okay, how about the intercept here? Well, you don't have to care about the intercept because this is just to adjust the average fitted probability to the proportions of ones in the data. Okay, and once the coefficients has been estimated, we can compute the probability of default. So this one is actually we kind of like predict. So let's say we have this person that files for an application for a loan, and this person has a credit card balance of 1,000. Before we do the prediction, let's look at this one. So we do not know the income of this person because this information is not given to us. So we only have the information on the credit card balance, and this person have a credit card balance of 1,000. Okay, so you can see that a few of them are actually defaulters, but mostly are not defaulters. So let us see what would the model suggest us to do. Okay, so the probability that the person with 1,000 in the credit card balance will default is given by, so you just plug in this information. So the exponent of, you can see beta naught plus beta 1 now both have hats because this is the estimated value. So the estimated value can be taken from this result. Okay, you should just plug in all the values and then you compute that the probability is 0.005. Okay, so there's only 0.5% probability that this person is going to be a default. So this is obviously much below 0.5 threshold that we made just now. So we will say that we will accept this person's application. So now let's talk about multiple logistic regression. So from the logistic function, we have the we have the logic function on the left hand side here, and here instead of having just one predictor we can have many, and to compute the probability instead of like this one where you only have like x variable here, in the multiple logistic regressions you have more than one variable, so that is the only difference. Okay, let's say instead of just having the balance, we also include another variable which is income and also the status. The status here is actually a dummy variable. Dummy means that it is equal to 1 if this is a student and equal to 0 if this is not a student. Okay, so we can see that the balance is significant. The income is not significant as we expected when we look at the scatter plot just now. And the status of a student is actually positive. Sorry, the p-value is actually significant. So if you look at the balance have a positive relationship with, with defaulting, because of course, the higher the balance will, the higher the probability of defaulting will be. And for the student, it is actually negative, okay? Because if you're a student, you are less likely to be a defaulter for some reason. Okay, so that is for the logistic regression. We're going to continue with the linear discriminant analysis. So if logistic regression involved directly modeling the probability of y based on x using the logistic function for the case of two response classes. Okay, now let us consider an alternative and less direct approach to estimate this probability. What I mean by less direct approach is that in the logistic regression, we have a direct approach to estimate the probability, where we directly estimate the probability of y based on the value for the x variable. However, for the linear discriminant analysis, we will use a less direct approach. And how? What does it mean by less direct approach? So, okay, the LDA actually, okay, the alternative way is to model the distribution of the predictors x separately in each of the response classes. What it means here is that let's say you have two response classes. Y has a two category, whether Y is defaulters or non-defaulters. Okay, so we will model the distributions of x separately for y equal to 1 and another distribution for x for y is equal to 0. Okay, and then we're going to use the Bayes theorem to flip this probability around to estimate the probability of y given x. So this is basically the definitions of the linear discriminant analysis. Okay, what is the advantage of LDA? So when the classes are well separated, it means that those with the higher credit card balance will be most likely to become defaulters. Because if you can see here, so this is what it means by well separated. Okay, if you look at the account balance here, those with a high account balance will be more likely to become defaulters compared to those with a lower credit card balance. So this is quite obvious and it is quite separated between each other. Of course, they are overlapping, but we can see a very clear pattern from here. So this is what it means. If the classes are well separated, the parameter estimates for the logistic regression model are surprisingly unstable. Okay, if the classes are well separated, the logistic regression is less stable. However, the linear discriminant analysis does not suffer from this kind of problem. A discriminant analysis involves deriving a variate, okay? And this discriminant variate, we call it as discriminant variate, is actually a linear combinations of the two or more independent variable that will discriminate best. Okay, it will discriminate between two groups or two or more groups between the objects of group defined as a priori. And discrimination means that you divide the group into this and that. Okay, so discrimination is achieved by calculating the variate's weight for each independent variable. Okay, it will calculate the variate's weight for each independent variable, like the balance just now, to maximize the difference between the groups. Okay, so it maximizes the differences between the group, which is the between group variance relative to the within group variance. So if you are so different from this group, you're going to be discriminated into that group. So this is what it means. Now let us look at this another example, okay, rather than the credit card balance and loan deferment just now. So the KitchenAid wants to determine whether one of its new product will be commercially successful. And they are interested to identify the consumers who would purchase the new product versus those who would not. So they want to minimize the number of errors it would make in predicting which consumers would buy the new food mixer and which would not. So they devised a rating scales on three characteristics of the new product, which is durability, performance, and style, to be used by consumers in evaluating the new product. So the primary objective of discriminant analysis is to develop a weighted combinations of the three scales, which is durability, performance, and style, to predict the likelihood that a consumer will purchase the product. So basically what it wants to learn is that which characteristic of its new product are useful in differentiating likely purchases from known purchases. For example, if the response would purchase is always associated with high durability rating, and the response would not purchase is always associated with low durability rating, then we can say that the durability is a good predictor in this discriminant analysis. Now, in evaluating the accuracy of our models, we have what we call as the confusion matrix. Okay. A confusion matrix is a table that is often used to describe the performance of a classification model or classifier. We call it, the classification technique is called classifier, on a set of test data for which the true values are known. It allows the visualizations of the performance of an algorithm. So we are going to do this confusion matrix in our lab sessions later so that you can see this more clearly. So before we do that, basically I just want to tell you one thing. Yeah. So usually when we want to do analysis, so let's say we have a set of data here. Okay. So N is, let's say, 1000. So the total number of the observations in this data set is 1000. And perhaps you want to divide the data into two parts, in which the first part is the trained data sets. The trained data sets is used to build the model. You build the model using the training data sets, and then you're going to have another set which you call as the testing data sets. So you build the model using the training data sets, and then based on this model, you're going to predict using the test data sets. So what you do in the test data sets, because you have the covariates x1, x2, and x3, and you also have the response variable y. Okay. So similarly, for this one also you have x1, x2, x3, and you have the the response variable, and you build the model based on this one. And then when you try to test this model, what you do is that based on the model that you developed using the training data set on the left hand side, you plug in this information on the x1, x2, and x3, and you try to predict what would be the response variable. And then you compare the estimated response variable, okay, estimated y, or we call it y hat. Y hat is estimated y. You compare this y hat with the actual y, and you want to see whether you correctly predict y hat. Is it similar to y or not? If it is similar, then we can say that you have predicted correctly. If it is not similar, then it means that you have done misclassification. Because let's say y is default this and y hat is non-default this. So you have miscorrectly classified this observation to become non-default this. So we're going to see more clearly in the lab session later, but basically this is what I want to say in this slide. The confusion matrix actually, it looks like this, but let me just finish this one. It allows easy identification of confusion between classes. For example, one class is commonly mislabeled or as the other. So most performance measures are computed from the confusion matrix. So if you want to compare the performance of different models, usually we use confusion matrix. So this is how confusion matrix looks like. So let's say on the column here, this is the predicted value. And on the row part, this is the actual value. So let's say if this observation is actually this class 1 and you predict it to be class 1, then this is a true positive. Okay, and if this the actual value for this observation is class 1, but from the model you predict it to be class 2, then this is false negative. And if the actual value for this observation is belonging to the second class, and you classified it to be belonging to the first class, then this is false positive. And this one, if you correctly classify class 2 as class 2. So this is a true negative. So from the confusion matrix, we can get the classification rate or the classification accuracy. So the accuracy is given by the true positive plus the true negative divided by all of it. Okay. And the precision is given by the true positive divided by the true positive plus false positive. Now we want to talk about sensitivity and specificity. So sensitivity and specificity are statistical measures of the performance of a binary classification test, also known in statistics as classification function. So the sensitivity, which is also called the true positive rate or probability of detection in some fields, measures the proportions of actual positives that are correctly identified as such. Okay, for example, like the percentage of sick people who are correctly identified as having the condition. So this is the true positive rate basically. Specificity, which is called the true negative rate, measures the proportions of actual negatives that are correctly identified as such. For example, like the percentage of healthy people who are correctly identified as not having the condition. So this sensitivity, the formula is given by the true positive out of all the positive. Or because the positive is consists of TP and FN. So, okay. And specificity is the true negative divided by all the negative. And because we know that N is actually Tn plus Fp. Okay, N is Tn plus Fp here. So this is the formula for sensitivity and specificity. And all this is actually used for to compare the performance of different models. So for example, in your project paper, you are asked to build several models and you want to compare the performance. So the first thing that I will ask you to do is first come up with this division. Some part of the data, maybe 70% or 80% or 50%, doesn't matter, you use for training data sets. You use to train the model. And you leave some part of it to become the testing model. Okay, we're going to do this in the lab session, but this is just to clarify to you. And once you get this from the test data sets, you're going to compare between the predicted value of y with the actual value of y. And from here, you should come up with confusion metric like this. And from this confusion matrix, you can compute the classification rate or the accuracy and precision, and also the sensitivity and specificity. So the sensitivity and specificity is also a tool which is required to build these ROC charts or ROC curve. So this is a receiver operating characteristics. This is one of the most important evaluation metrics for checking any classification model performance. The ROC tells us how much model is capable of distinguishing between classes. How much of the model that we compare is able to discriminate or distinguish this group belong to this group, that group belong to that group. So the ROC curve is plotted with total positive rate against the false positive rate, where the total positive rate is on y-axis and the false positive rate is on the x-axis. Okay, so this is TPR and FPR here. And when the two curves don't overlap at all means that the model has an ideal measure of separability. It is perfectly able to distinguish between positive class and negative class. So here, okay, this is how ROC charts should look like. So the dot line here is actually the baseline. If your model is just on top of this baseline, it means that your model is not performing at all. Okay, you better have random guesses instead of building the model. So if your model is very close to this line, to this diagonal line, it means that your model is not good at all. However, if your model is going up as much further from this line, okay, just like the green line here, it means that this model is good in distinguishing between the classes. And if let's say you have two models in your project, you might have two or more models, okay? You can have two or more ROC chart here, and then you compare which one is better, which one is further away from this baseline. Okay, next I'm going to talk about quadratic discriminant analysis. The difference between linear and quadratic discriminant analysis is that, okay, number one is QDA classifier results from assuming the observation from each class are drawn from a Gaussian distribution and plugging this estimate for the parameter into Bayes theorem in order to perform the prediction. So this sounds like linear discriminant analysis as well. However, unlike LDA, the QDA assumes that each class has its own covariance matrix. So the LDA, it assumes that they share the same covariance matrix. The QDA assumes that each class has their own covariance matrix. So the QDA assumes that an observation from the kth class, let's say you have 1 to 3 class, so any observation from any class is of the form of X, which is normally distributed with the mean of mu of K, where K is equal to 1 to 3 if you have 3 categories, and the sigma of K. So this one is a normal distribution, the Gaussian distribution. Normal distribution have a mean of mu K and the variance of sigma K. But because this is this is a multivariate, so sigma K is actually the covariate matrix for the kth class. So each of this is belonging to, each of this X is belonging to which class, okay? And each of the class have their own covariant matrix. Now, there's a bias variance trade-off between the LDA and QDA. Of course, LDA is much simpler and QDA is more complicated. So, to answer this question with P predictors, how many predictors you have? If P is equal to 1, you have 1 predictors. If with P predictors, estimating a covariant matrix requires estimating P times P plus 1 divided by 2 parameters. And the QDA estimates a separate covariant matrix for each class for a total number of K times this parameter. So it will be many more estimation needs to be done if you use QDA. So by instead assuming that the K classes share a common covariance matrix, the LDA model becomes linear in X, which means that there are K times P linear coefficients to estimates, which is obviously much lower than, than this one, than QDA. So as a consequence, LDA is a much flexible classifier than QDA. And so it has substantially lower variance. This can potentially lead to improved prediction performance if you want to focus on the variance. But if the LDA's assumption that the K classes share a common variant matrix is badly off, then LDA can suffer from high bias. What it means here is that if the covariant matrix is not the same, and it is totally not the same, then we can have a biased results for the LDA. So roughly speaking, LDA tends to be a better bet than QDA if there are relatively few training observations, so reducing variance is crucial. Okay, in contrast, the quadratic discriminant analysis is recommended if the training set is very large. So let's say you have a very large training set or very large data, so that the variance of the classifier is not a major problem. So, or if the assumptions of a common covariant matrix for the K classes is clearly untenable. So this, if you have any of this, characteristics, if your training set is very large, if the variance of the classifier is not a major concern, or the assumptions of the common covariant matrix for the case classes is clearly untenable, then you can use the QDA. Okay, that's all for this lecture. So in this lab session, we are going to examine some numerical and graphical summaries of the S-market data. So this S-market data, you can get it from the library ISLR. So what I'm going to do first is I just going to load the data, load the library ISLR, and we can run any functions that we want. But for this exercise, I'm going to run this function names of the S-market just to give me the names of the variable that we have in this data set. So we have year, we have leg 1 until leg 5, the volume, today, and direction. So basically this data consists of the percentage returns for the S&P 500 stock index over 1,250 days from the beginning of 2001 until the end of 2005. So for each date, we have recorded the percentage returns for each of the 5 previous trading days, which is denoted as leg 1 to leg 5. So leg 1 means that this is the yesterday's trading, and leg 2 is 2 days ago, and we have up to 5 days ago. So we also have the volume, which is the number of shares traded on the previous day. So this is the number of shares traded. And we have the variable today, which is the percentage returns on the date in questions. And finally, we have the direction, and this direction is actually categorical. We only have 2 categories, whether the market was up or down on this date. So we only have 2 values for this one, up and down. So let us just run another function, dim, where dim gives us the dimension. So here we have 1,250 observations over 9 variables. And I just want to run the summary function. So the summary function tells us that year we have from 2001 until 2005. And then we have informations on the leg 1 until leg 5. And if you look at the summary statistics, you can see that they are almost the same. So the percentage returns for the 5 previous trading days is between -5 to the maximum of about 6. And they are almost the same for each of these legs. And the volume, which is in billions, the minimum is 0.3 and the maximum is 3.15. And we have today, which is the percentage returns for today. And this is the direction, which shows us that compared to yesterday, which is leg 1, to today, which is the percentage return for today, whether it goes up or it goes down. So basically that is that. Okay, so next is I like to find out the correlation between, especially between today's percentage returns with yesterday and 2 days ago and 3 days ago and so on, and perhaps also with the volume. So basically we want to find out what is the correlation between all of this numerical variable here. So if we just run the function core, which is for correlation, you will find an error, because the problem is that it must be that one of the variable is actually categorical. So basically you can't find the correlation matrix if your data sets have a categorical variable. So next what we do is we find the core of the S market, but this time, I hope you still remember how to use the square bracket. This square bracket, and on the column part, we put -9, which means that we remove the ninth variable. So without the ninth variable, which is categorical, we are able to find out the correlation matrix. Okay, and this correlation matrix is actually symmetrical because, for example, this one 0.029 is exactly similar to this one because this is the correlation between lag 1 and year. And if you look at the correlation value between all this, okay, between each of this variable, you can see that the correlation is very small. It's very close to zero, whether it's positive or negative. Like for this one, it is negative, but it is very, very close to zero. And this one, 0.029, is also very, very low. So what you can say is that the relationship between yesterday and 2 days ago is low, and the relationship between today and all of the other lags here, okay, is also very low. It's very close to zero. So what intuition can we get from this one? Our goal here is we want to use the information about the percentage returns of 5 previous days in order for it to be able to tell us what would be the direction for today. Okay, so based on 5 days ago, we want to predict whether today is going to be up or it's going to be down. So, however, if we look at this correlation, it seems like this is an impossible task because today's percentage return does not have any correlation with the previous 5 days. What it means here is that if yesterday's goes up, we can't really be sure whether today is going to be up or down. Okay, so that is the problem with this prediction goal. Okay, but nonetheless, what we are trying to do next is this is just a correlation. But what we are going to do next is we're going to fit a classification technique and see if our classification technique can improve the prediction accuracy. Okay, now next line is I just use the attach. If you're not sure what is the attach, I think you have to go back to the data manipulation. And next is I just use the function plot for this volume. Okay, before I explain about this plot, one thing I forgot to mention is that if you look back at the correlation matrix, you can find that the only high correlation is between year and volume, which means that because the volume is actually the number of shares traded on the previous day in millions. So this is the number of shares. This is not like the other variable. The other variable of the percentage returns. So this is the number of shares traded on the previous day in billions. So over the years, we can see that the number of shares traded is increasing. So as you can see from this plot, from day 1 until day 1250, it increasing, especially nearly at the day 1000. Okay, so however, we are not particularly interested in looking at this one because what we want is we want to use all this information in order for us to predict whether the direction here will go up or down. Okay, so volume might play a role, but that is not our particular interest for now. Okay, now comes to the most interesting part. So next is we're going to run this logistic regression. And for the logistic regression, we use the GLM function. So if you type in the GLM function here, okay, so this is to fit the generalized linear models. So GLM is used to fit generalized linear models, specifying by giving a symbolic description of da 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 da. I'm not going to talk about this, but basically the GLM function syntax is start with a formula, and the formula that we have here is exactly the same like we use in the linear regression, which is first we have the dependent variable or the response variable or the y variable here is kind of like regress using the tilde symbol here, regress against leg 1 to leg 5 and volume. And then we have the second syntax here, we should have the data. So the data is based on the ESMA CAT data. And the most important thing here is, okay, I'm going to find it somewhere here, the family, okay, method. Okay, we're not really actually using this one. Okay, basically, if you want to have a logistic regression, you should put a family equal to binomial. Okay, because this GLM can be used for many. Yep. Okay. This is a description on the family. So if you want to see other type of family other than binomial, you can just click this one. So we have Gaussian, Gamma, and Poisson, and some other family members. But here, because we want to use a logistic regression, so family is set to binomial. So one thing that you need to remember in this class is that we don't use any other family here. So whenever you want to run a logistic regression, the only thing that you should remember is this one, is this part. Okay, family is set to binomial. Okay, now we store all this into this one, this object, which we call as glm.fits. And now we want to get the summary of glm.fits. So this is what we get. So, right. So this is the coefficient estimates. We have the coefficient estimates for the intercept, leg 1 until leg 5, and also the volume. So if you look at I just pick one, which is the coefficients for leg 1. And this is negative 0.07, which tells us that if yesterday's percentage return is positive, then today is going to be down. Today it's going to be, negative, because the coefficients here is negative. So what it means here is that if today's was doing good, then today we will expect it to be bad. All right. However, if you look at the p-value, it is not significant. In fact, none of the variable that we have here is significant. Okay, they are very big. If you look at the standard error, they are very small against the z value, which is relatively big. So none of this variable is actually significant. Okay, in the next few lines, I just want to show you on how to extract the coefficients from the glm.fits. So there are 3 ways of doing that. We're going to run off all of them and see the difference. So the first one is that if you're only interested in looking at the coefficients, okay, and you just want to find out what is the coefficients without all the other informations. So instead of having to type in summary of GLM fits, you can just type in coef of the GLM fits, because coef is actually one of the things that we save in glm.fits. Or if you want to have the coefficients with the standard error, z value, and the p-value, but without all the other bunch of things, you can just type in summary of the glm.fits and $sign coefficients. Okay, so this one you just get the informations for the coefficients without all the other information. And this is summary.glm.fits also, but here you have a $sign of coefficients, and within this you have comma 4, which means that for these coefficients you only want to list down the p-value, because p-value is located in the 4th location. So the first location is the estimates, and you have the standard error and the z value, and finally you have the p-value. So this is not important. This is just, different ways of showing the same thing. Okay, so now we want to predict. Okay, so we want to predict using the predict function. What we have here is we already have this model, which is obtained from the GLM function, and we save this into glm.fits, and we have already looked at the model using summary of the glm.fits. Now we want to predict, because before we do that, I just want to run S market 1, 2, 3, for example. Okay, oops, 1, 2, 3, and that's it. So this is the first three information in the original data sets that we have. So this is the information on the leg 1 to leg 5 and the volume, and we have the direction. For the first two is up and the third one is down. And I run again this one. Okay, so this is the coefficient. So this is the coefficients for the first leg, coefficient for the second leg, and so on. So basically what we're trying to do here is that based on the information for the first observation here, based on this information that I highlighted here, if you plug in this information into this model, okay, this model that you have developed, then you're going to predict whether its direction is going to be up or down. So basically what you want to do next is you want to know, based on this information, what is the probability that it is going to be up. Okay, so that is what we are going to do here. We use the predict function on the glm.fits, which means that you tell R, hey, I have this model glm.fits. I want you to predict based on this model, where the type response is when you want to tell me what is the probability that is going to be up. Okay, that is going to be up instead of down. All right, and you can store this probability, and you must remember that the probability range between 0 and 1 with any numbers close to 0, which means that there is a low probability. Any numbers close to 1 means that it is high probability, and you will store this probability into glm.props. Okay, so now we want to have glm.prop maybe from 1 to 3 instead of 1 to 10. Oh, okay, there's an S there. As you can see here, okay, so the first probability is 0.507, which is quite high chances, above average. So what it means here is that based on this information, and you plug in this information, you don't have to care about what is the actual value, whether it's up or down. Okay, so what you care is that based on this value, and you plug in into this model, and you predict that the probability that it's going to be up is 0.507. Okay, and the probability for the second one, which is based on this value, the probability that it's going to be up is given by 0.48. And so on. And for the third one, based on this information, the probability that is going to be up is 0.48, which is very close to the second one. However, the actual value for the second one is up, while the actual value for the third one is down. So we're going to talk about this again, but just keep this in mind first. So first is we run the contrast of the direction, just to know how many different categories are there for the direction. So this is the actual data, okay, not the predicted one. So for the directions, we have up, which is equal to 1, and we have down equal to 0. So basically, this is when you do the logistic regression, you need to know which y is equal to 1, which y is equal to 0, because our prediction is based on y is equal to 1. So here, y is equal to 1 when it is up, and y is equal to 0 when it is down. Okay, next is, this can be a little bit confusing, but just bear with me for a while, okay? So what we are going to do next is, we have this probability, And we want to classify this probability, which means that for this exercise, for now, we're going to use a threshold value of 0.5. Okay, the thing with 0.5 is that I'm going to make this bigger. Okay. So any the probability if y is how do I want to write this? So if the probability of y is larger than 0.5, or you can put larger or equal to, doesn't matter, okay? It's larger than 0.5, then we're going to classify it to be up. If the probability of y is less than 0.5, then we're going to classify it as down, okay? So first is we want to create a new variable, and this new variable name is glm.pred. Okay, so we want to have glm.pred is equal to up if the predicted probability is larger than 0.5, and we want it to be down if the probability is less than 0.5. So for the first observation, we want it to classify it to up. The second and third, because it is lower than 0.5, we want to classify it as down. So let me do this first, okay? So glm.pred, we want to repeat down 1,250 times. So what we do here is that we just list down for 1,250 times. If you want to ask me why, okay, let's go to the next one, okay? And then we replace if the glm.props, which is the amount, or which is the probability here. So this is the first three observation in glm.props, okay? So if glm.props is larger than 0.5, then we're going to replace glm.pred with up, because all the values just now was just down. You have down, 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 down for one from the first observation until the 1,250 observation. And now if the glm.props is larger than 0.5, you're going to classify it as, you're going to replace it with up instead of down. Okay. So now let us just type in glm.pred or 1 to 3. As you can see here, it depends on the value of glm.props. If it is larger than 0.5, it is up. If it is less than 0.5, it is going to be down. Now, if you look at the actual value, okay, number one is up, up, and then down, but we predict it to be up, down, and down. Okay, so here, 2 times, the first and the third observation, we predicted correctly, but for the second observation, we have wrongly predicted it to be down, while the actual value is actually up. So this is this involves in the accuracy of the models. So if I ask you, if you look at today's weather and yesterday's weather, and maybe up to 5 days ago, what would you predict tomorrow's weather? Some of you might say that, oh, tomorrow is going to be raining because it has been raining for 3 days. And some of you might say that, oh, because it has been raining for 3 days, tomorrow will be sunny because there is no more rain in the cloud. Okay, so tomorrow we look at tomorrow's weather, and it is actually snowy. Okay, no, it's actually rainy, and some of you might get it wrong. So basically, this is just a prediction. This is just your prediction. So you predict it to be wrong, but some of you predict it to be correct. So the prediction is not always similar to the actual. Okay, so now we want to know, okay, maybe next is I want to table the glm.pred. Okay, there's a 900 100 over 900, almost a thousand, which we predict to be up, and 286, which is a down. Okay, so it is good if we can tabulate between the GLM.pred and the direction itself, between the predicted and between the actual value. So here on the column part, we have the up and down for the actual, and on the row part, we have the predicted. So 145 observation, the actual value is down and we predict it to be down, and 507, the actual is up and we predict it to be up. So this is the thing that we have correctly classified. However, we have made an error for this part, which is actually down, but we predict it to be up, and for this part, which is actually up, but we predict it to be down. So now we want to compute the misclassification rate. Misclassification rate. So misclassification rate is 507 plus 145. Okay. This is not misclassification rate. This is the correctly, okay, please ignore this one. The misclassification rate is actually 457 and 141. Okay, so please ignore this one. So we just want to know what is the value, or what is the percentage that we have guessed correctly using this model. So this is 507 plus 145 divided by the total observations of 1250. So we correctly classified it 52% of the time, which is just slightly above average. Okay, so which means that we can make a guess, or we can make, based on this model, we are only able to make a prediction which is accurate 52% of the time, which is not very good. This is just above random guessing. Right. So another way of doing this is that instead of computing one by one, you can just get the mean if the GLM.pred is equal to direction. So if the GLM.pred is up and the direction is up, or if this is down and the direction is also down, and you're going to compute the mean. So this is a mean for categorical variable, and usually the mean for categorical variable will give you the percentage. So the percentage is 52%. This is just like, if you have 5 females in the class and 5 males in the class. So if you compute the mean, it will be 0.5 for each of the gender. Okay. All right. Now, what we're going to do next is, all right. Okay, just now what we did was we use all the data that we have, a total of 1,250 data, and we built the model based on this data, and we make a prediction based on the similar data. We make the prediction for all the 1,250 data. Okay, and then we compare it against the actual value in that data sets. So what we're going to do next is we're going to divide this data into 2 parts, which is one part we use for train. It's like you train this model using the training data sets, and you don't touch on the part where you divide the data into testing data sets. Okay, so this is the part that you use for building the model, and this is the part where you use to test the model. Okay, so in the practice, usually some people use many different composition, Okay, some of the researcher might want to use 70% for the training data sets and 30% for the testing data sets. Or you can change it like 80% for training, 20% for testing, or 50-50. And some of the researcher have three stage where they have the third part, which is called the validation. So when you involve validation, which means that first you have a training data set and you train your model using the training data sets. And then you validate and improve your predictive performance using the validation data sets. And finally, you use the test data sets to test whether your model is doing good or not. Okay, so the intuition behind this is that you only use this training data sets to build your model. And for these testing data sets, you remove the response variable from the testing data sets and you use the information in the testing data sets to predict what would be the response variable. And then you're going to compare the response variable that you predicted and compare it against the actual value of the response in the test data sets to see. So basically the intuition behind this is that if your model is good, okay, that you use the information in the training data sets and you have developed your model, if your model is good, then it's going to perform similarly good to a new data sets that were not included in the model building. So this is what we are going to do next. So instead of there are many ways of doing this. As you can see, I remember in the last lecture, we use some percentage amount of our data sets. Like we use the sample function to divide the data into training and testing data sets. There are many ways of doing this, but in this exercise, I'm going to show you quite not a conventional way of doing this division. Okay, so we're going to have a training and a testing data set. And here the training data sets will be named as train. Okay, so if you look at the year, I just want to table year. We know that we have about 252 observation for each of the year except for 2001, where we only have 242. So we want to use all of the observations from 2001 to 2004 as our training data sets. And we're going to keep the 2005 observations to be our testing data sets. Okay, so instead of randomly pick from randomly the observation within each year, we're going to use 2005 for testing and the rest of the year as the training data sets. So this is different from the way how we did the division, how we divide the training and the testing data set before. So now let us just run train is equal to if year is 2005. So basically, if you want to know what is the value for train, I just want to list down from 1 to 10. So if this observation belonging to the year before 2005 is going to be true, and if you type in table of train here, so false is 2052, which is belonging to the 2005 data, and the rest are true. Okay, so the train only have a true or false value depending on whether the year is less than 2005. So next is, okay, this is going to be a bit, I'm going to delete this. SMarket 2005. Okay, so SMarket.2005 is a new data set. And this is a copy of this original data set where it is not equal to train. So if train is false, then it's going to be copied into SMarket.2005. So you can run the dimension of 2005. You can see that you have 252 observation. And if you type in table of SMarket 2005 $year. There's only 1 year, which is 2005. Sorry, my voice is not really good right now. It's 4 in the morning, and because this is Ramadan and this is a video lecture which is made during the COVID-19 pandemic, and I tried to record my video since several days ago during the day, and I get so thirsty. At night I get so tired because I've been fasting for the whole day, and after eating I just collapse. So this is the only time that I can record this video lecture, so I'm sorry with with the quality of my voice. I'm definitely not Siti Noharliza. Okay. So I hope you know that in the SMarket 2005, this is actually the testing data sets. Well, let's remove this one, okay, because this is not 30%. This is not 70 and 30. So this is basically for the year 2005, and this is for the year 2001 until 2004, right? Okay, and then we're going to have a new variable, direction 2005, which is a new vector here, is equal to the direction when train is false, which means this is the direction for the year 2005. Okay, so you can type in the direction of 2005 here, and just I can just type in one thing. Okay, head of direction 2005. Okay, so the first 6 observation is down, 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 up, down, up. Okay, and then what we're going to do next is, now we have the training data sets and the testing data sets, and the testing data set is SMarket 2005 here. I'm going to remove this. It might not seem clear to you right now, but please bear with me. So here is, this is quite mouthful. Okay, I'm going to run this so it looks more structured now. Using the GLM function on the direction, regress against leg 1 to leg 5 and the volume, and the data is SMarket and the family is binomial. But now we have a subset. Okay, so basically what it means here is that we built this model based on the training data sets. Remember that the train is true if the year is between 2001 until 2004, right? So we just built this model based on these training data sets, and we store it in glm.fits. Okay, next is we're going to make a prediction. So this predict based on the glm.fits here, which is this model, and we're going to predict for the testing data set, which is this one, the 2005. We're going to predict for the SMarket.2005, which is the testing data set, and the type is similar, which is the response, which gives us that the predicted probability. Okay, remember that this is a predict based on the glm.fits here, okay, based on the SMarket data, where the type is response, which gives us the predicted probability. And we're going to save this into glm.props. Well, it doesn't matter if this name is similar to the previous one that we have done. We're not going to look at the previous one again, okay? So what we'll do is that if you have 2 names here, this name is similar to the previous one, we'll just replace the previous one. Okay, so again, now we have glm.pred, which is a repeat down for 252 times, because in this testing data sets we have 252 data. And then we're going to replace GLM.pred with up if the GLM.props is larger than 0.5. So I've explained about this previously. I'm not going to do it again. And next is we want to make a cross tabulation between GLM.pred and the actual value of the direction. So on the column part here, we have the actual value. So you have correctly classified 77 and 44 here, but you have incorrectly classified 34 and 97 here. Okay. And next is we want to know the correctly classified one, which is 48%, which is low because you can correctly classify 48% of the time. And the misclassification rate is 51%. Okay. So the results are basically rather disappointing. The test error rate, which is about 51.9%, which is worse than random guessing. And of course, this result is not at all surprising, given that one would not generally be expected to be able to use the previous day's return to predict the future market performance. If you're able to do that, then, you know, some of us who are very good with statistics can be very rich right now. So we recall that the logistic regression model had a very underwhelming p-values associated with all of the predictors. If you remember, we ran the summary, we look at the p-values of our logistic regression just now, and none of the p-values are actually significant. So perhaps by removing the variables that appear not to be helpful in predicting direction, we can possibly obtain a more effective model. Okay. So let us look at this one. Let us just build another model, and this time, okay, before we do that, I just want to get the summary of the GLM fits here. So summary of GLM.fits. Okay, we look at the p-value here. None of the p-values here are actually significant, but at least you can see that for leg 1 and leg 2, the p-value is smaller compared to the others. Okay, so we probably want to remove all the variables that are, you know, that have no relationship with the response variables. And this may cause a deterioration in the test error rates. So we're going to refit the logistic regression using just leg 1 and leg 2, which seem to have the highest predictive power in the original logistic regression model. So we're going to run this GLM function. And here we have direction against leg 1 and leg 2. Again, from the data as market, the family's binomial subset is trained. So this is done using the training data sets, and we save it in, the same name, glm.fits. So what it will do is that it will replace the previous results. And then can I have the function predict to predict based on the glm.fits on the testing data sets, and the type is response. And first, again, okay, we do this again and again. We're gonna repeat down for 252 times, and we're going to replace glm.pred with up if the probability is larger than 0.5. And now we're going to tabulate between the predicted and the actual value. And now the probability that you're going to get it right is 56% of the time, which is a huge improvement compared to the previous two models that we have run before. So you have correctly classified 35 and 106, which is 56% of the time. So we see a huge improvement here in the logistic regression. if you only use two variable instead of using all of the variable that we have just now. Okay. And finally is we want to try to predict for a particular amount of or the particular value for leg 1 and leg 2. Let's say the first leg, okay, you have 1.2 and 1.5, and the second leg you have the amount of 1.1 and 0.8. And based on this particular value, you want to predict what would be the probability that is going to be up or is going to be down. So here is, we're going to run this. We're going to predict based on the glm.fits. And this one, the new data, we're going to predict this based on the new data. And this one is the data.frame for leg 1 and leg 2. And you actually use the C function to input the value for leg 1 and the value for leg 2, where the type is response. So you have, you will come up with the results for the, for the probability. And the probability that the first one, based on the value of leg 1, 1.2 and leg 2, 1.1, the probability that is going to be up is 0.47. So if we classify this, so we will predict it to be down. And if leg 1 is 1.5 and leg 2 is negative 0.8, so we would predict that the probability that is going to be up is 49%, which by our threshold 0.5, this would be classified as down. So we continue again, and this time we will do linear and quadratic discriminant analysis. And because I've already closed R before, so I need to run a few things once again. For example, I'll run the library, get the S-market data, and probably I just run some dimensions that the S-market is already there. And I think I need to attach the S-market. And there are a few things that I need to do. Number one is I need to create train here and create a new vector as market.2005, which is equal to this one, which is not the training set, because as market 2005 is for the testing data sets. So because I have already explained this before, I'm not going to talk about it again. And lastly is the directions of 2005, where this is actually the actual value of the direction in the year 2005, which we choose these data sets to become the testing data sets. So I think that's all for now. And now let's go to the linear discriminant analysis part. Okay, for this one, because we are going to use the LDA function, and these LDA functions come from the library mass. So first we need to load the library, and we will use this LDA function for the response variable directions against leg 1 and leg 2. And the data here is the S-market data. And again, because we want to run this function to the training data sets, so we put subset equal to train here, and everything will be fit and stored into LDA.fit here. So all the outputs will be stored in this one. So let us just call the LDA.fit. So I'm going to run this one. So first is we know that we use the function LDA, and these are the variable involved and the subset involved. So basically, the first thing that we see is the prior probabilities of the groups. So what does this mean? So you need to remember that we have the data from 2001 until 2004 for this training data set. And based on this, the prior probabilities tell us that 49% of the data from 2001 to 2004 is actually down, and 50.8% are actually up. So this is just the probability, this is the mean of the ups and down in the variable direction in the training data sets. And then the next thing we see is the group means. Okay, so the group mean, basically we look at one column first. For the first column, which is leg 1, so the average of leg 1 belonging to the down group is 0.0042. So this is the average percentage return for leg 1 that belongs to the group down. And we would say that the average of leg 1, the percentage return of yesterday belonging to the group up is negative 0.03. So similarly, we can see that for leg 2, this one is positive and the other one is negative. So basically, what does it mean? Okay, it means that if today is down, if the market today is down, then the information that we get is that the average of yesterday's return is actually positive. And if today is up, then the average percentage return for yesterday is negative, and even 2 days ago. If you see that 2 days ago the average return is negative, then it is quite safe to say that today it is going to be up. While if 2 days ago it was positive, then we could say that today is probably going to be down. Okay. And lastly, we see the coefficients of linear discriminants. So basically, these coefficients is the coefficients for this model. These are the multipliers of the elements for the linear discriminant analysis. I'm so sorry, my voice has become croaky right now. Okay, so now we have already looked at the model at the output, and now I just want to run this function plot. Okay, figure margin too large. I believe that we have to do something here. So this is what I usually do. I just use this one. If there's an error in the plot new, what I did just now was I just copy this thing and I brought it to Google, and Google gave me the answer, and I just run this, and it should work perfectly after this. Trust me. Okay, so basically what does this plot means? All right. So this plot is actually the linear discriminant. This is for the up, the direction equal to up, and this is the direction equal to down. Okay, so I'm not really an expert in this kind of graph, so I just make a pass on it. So basically our interest is to make prediction, and we want to come up with the confusion matrix and to see if this LDA perform better than the logistic regression we did just now. So next is I'm going to use the function predict, and this is to predict based on the LDA.fit, and this time we're going to use the testing data sets to predict, and we're going to store this output into what we call as LDA.prep. Okay, so now the next thing is that I call all the names of the items that we have under LDA.pred, and basically in LDA.pred we have the class, we have the posterior information, and we have the value for the x. Okay, and we are particularly interested in looking at class because class will classify the probability whether we predict it to be up or we predict it to be down. So next is I'm going to create a new vector. We name this as LDA.class. Okay, and this LDA.class is equal to the LDA.pred $ class. Okay, so let's look at just a few, just a few of the observations under LDA.class. So as you can see, the first 6 observation is up, and I believe that there are some which are down. Well, the next thing we do is we want to tabulate this. So this is the confusion matrix. We want to tabulate this, the LDA.class, which is the predicted classifier, to the actual value of the direction. Okay, so the actual is on the columns and the predicted is on the row. We see that 35 and 106 here are correctly classified. So next is we're just going to run the mean, and this is the mean if the LDA class is similar to the value in direction 2005. So this is actually 35 plus 106 divided by the whole observation. So you get 0.559. So you can say that 56% of the time this LDA classifier can correctly predict. If the market is up, it can predict the market is up, and vice versa. Okay, the next is you're gonna run this. So this is just to get the okay. Let me just run this to line first, and let me explain. Now we are particularly interested in this, but in this line we are looking at LDA.pred $ posterior, and previously we're looking at LDA.pred class, and this time we are looking at posterior. As you can see, let me just revise again. So under LDA.pred, basically we have class, we have posterior and X, and just now we're looking at LDA.pred class. So let me just run head of LDA.pred class. So the first 6 observation is classified to be up based on the LDA models that we created. And then next is we're going to use this LDA.posterior, and let's just see the first few observations under this one. Okay. So the first 6 observation is this one. So the observation number 999, you need to remember that this is the observation in 2005. So this is the 999th observation out of the original data set. And the probability that it will go down is 0.49, and the probability that it goes up is 0.509. And in the second one, you can see the probability of it's going down and going up. And for this one, it happened to be that it corresponds to this LDA.pred class. Okay, because for each of this, we can see that there's a higher probability that they are going to be up instead of down. And you can see that in the class, they are up. Okay, however, let me just run something, just to check. If I type in table of LDA.pred and I put their class, okay, 70 of them are down and 182 of them are actually up. Okay, so here it is. This book, because I just copy everything from this book, so actually it might be confusing, so I think it is my responsibility to explain it to you, because this is in the book. So basically, if you look at this one, this LDA.pred $posterior, and this is correspond to the first column, and the first column is that it is correspond to the down column. Okay, so we would expect that if this value is larger or equal to 0.5, then there are 70 observations here. But this one, it is larger or equal to 0.5, means that they have more probability of going down. Okay, because we are looking at the first column, not the second column. So because I didn't change this, because this comes from the book. If I were, I would change this to become 2, so it might not be very confusing. But if you look at this, this is very straightforward. Yeah. So this is corresponding to the first column here, which is down. And if the probability of being down is larger than 0.5, then we would say that we would predict it to be down. So as you can see here, there's 70 observation here. Similarly to the information in the LDA.pred $class, the number of observation belong to the down predicted value is 70. And the other one is 182 and 182 here. Okay. All right. So I'm going to skip this particular line, because I've already explained about it, and also this line. So basically, our next question is, suppose that we wish to predict a market decrease only if we are very certain that the market will indeed decrease on that day. Or okay, let's set the probability to be very high, at least 90% instead of 50%. Instead of using a threshold of 0.5, now we want to use the threshold of 0.9. And instead of predicting up, now we are going to predict whether it's go down. Okay, maybe you want to avoid the risk. You don't care if it is go up, but you don't want it to be down, right? So with 90% of accuracy, what can you do? How can you predict that? So I'm going to run this one. So basically, what does it mean? Okay, We're looking at the LDA dot Pratt dollar sign posterior, and we're looking at the first column, which corresponds to the down column. If the probability of going down is larger than 90% or is larger than 0.9, how many observations are there? Unfortunately, the observation is 0%. Okay, so if you are interested, you can look at the further explanation from the book. It's quite interesting, actually. So okay, so the next one is I'm going to finish off with the quadratic discriminant analysis. I'm going to run this very quick. Okay, so here, instead of using the LDA function, we use the QDA function, which stands for the quadratic discriminant analysis, and everything else is the same. And let's just pick on the results. Also, you have the prior probabilities here, and you have the group means here, and we have already talked about this. And our interest is to make a prediction based on the testing data sets. And then we're going to make a confusion matrix between the predicted value and the actual value. And the utmost interest is on the classification rate. What is the percentage that we make a correct classification? So here, the QDA, we can see a huge improvement compared to LDA and also the logistic regression. Here, almost 60% of the time, we are able to make a correct prediction. And this is actually remarkable because for the stock market data, for the market data, actually, it is extremely difficult, almost impossible to actually predict what's going to happen to the market today or tomorrow. Okay, so I think that's all for the lab session, and I'm going to end this session.